Alrighty, in this video, we are looking at solving by taking roots. Our objectives are to solve quadratic equations by taking roots, to simplify radicals, including those with negative radicands, and to solve real-world applications involving quadratic equations. So let's get started. We have seen equations that look like this, equations of the form x squared minus c equaling 0, where c is a perfect square. And we can use previous methods. Let me show you what I mean. Let's say that 81 is our value of c. 81 is a perfect square, and therefore we can use that the x factor to find our binomial factors here. Our b value is going to be 0 because there is no b value. The product of a and c is going to be 1 times negative 81, which is negative 81. And we're thinking of those values to put in the wings that multiply to give you negative 81, but add to give you 0. Well, that would mean they'd have to be opposites of one another to give you the sum of 0, and that's going to be negative 9 and positive 9. So our two factors are x minus 9 and x plus 9. You could FOIL that and simplify, and you would see that it would take you back to the original problem. But we're not quite done yet. We need to apply the zero product property and set the first and second term equal to 0, so that we find x to be 9 and negative 9. Those are the two values that make that statement true. But today I'm showing you a new method, another method, and it is taking the square root. To do this, we'll first isolate our squared term by adding 81 to each side. Then we'll take the square root of each side, square rooting x squared and square rooting 81. Now this I wrote down as remember, but it might be brand new to you. You may not have seen this property before in Algebra 1. The square root of x squared actually means its absolute value. So really we're looking at the absolute value of 9. And that would, the absolute value of x giving you 9, I'm sorry. And if we solve that, x could be 9 or negative 9. Same result as in that other method, but we're going to see that this square root method has many applications that are going to be very helpful. I want to talk to you a little bit about simplifying radicals. We've been reviewing this, but let's recall that this radical here is not a perfect square. It could be factored, and so we would factor that number inside, which is called the radicand, into its prime factors. You could do your prime factoring tree, and you would find it to be 2. You'd have 3 3s, and you'd have 2 5s. Those are the factors of 450. Now, we've kind of talked about this. It sounds maybe a little silly, but because there are 2 3s, one of them kind of sacrifices itself to come outside, as does with the 5, because they have partners. But essentially what's happening is squaring a square, square rooting a square, it allows it to come outside, which looks like 3 times 5 on the outside, and square root of 2. 2 was not able to come outside because it did not have a friend. It was not squared. And then we can simplify, and that gives us 15 times the square root of 2. That is simplifying radicals, and We're going to do that a lot in the coming lessons. We'll also be rationalizing denominators. What I mean by that is, really, this can be rewritten as the square root of 5 over the square root of 3. You can distribute the radical to the numerator and denominator. But the square root of 3 is an irrational number. We don't want radicals in our denominator, so we have to multiply to make the radicand a perfect power, a perfect square. So what could you multiply the square root of 3 by so that you're taking the square root of a perfect square? You could multiply it by itself. This is really nice because we'll just look at that denominator and emulate that, but we have to multiply it by square root of 3 over square root of 3 because we don't want to change the value of our expression. And the square root of 3 over the square root of 3 is 1. Watch what happens when we multiply here. We would have in the numerator the square root of 15 over the square root of 9. If you simplify, that gives you the square root of 15 over 3. So in multiplying our original by the square root of 3 over the square root of 3, we didn't change its value. And you could check that by plugging in both of those expressions, the original and this result. You'll get the same decimal approximation. But what we've done is made a rational number in our denominator. We no longer have a square root. Now, there was a gentleman, you've probably heard his name if you've taken geometry, Euler. He was a famous mathematician and he tried to solve this problem. X squared plus 1 equals 0. And he, like you're probably anticipating, subtracted 1 from each side, took the square root of each, so that's the absolute value of x, equals the square root of -1. So you would have either positive or negative square root of -1, but there is no number in our system that we've studied so far that you can take the square root of -1 and find it to be some value. You can't take the root of a negative number and get a real number. What you get is imaginary. The square root of a negative number is not a real number. We call it imaginary, and I'm not joking. Let me show you in this definition here. The imaginary unit, and we denote it with an I, is the square root of -1. I equals the square root of -1, or if you square each of those sides, I squared equals -1. This is the unit that we're going to be working with if you have roots of negative numbers. Let me show you in this example here. We're going to solve this, and our answer is going to have an imaginary part to it. So let's get started. We're going to isolate the squared term by subtracting 45 from each side, and then we'll apply the square root property and we'll take the square root of each. If you take the square root, then you're looking at the absolute value of z, which means you could have either positive or negative square root of -45. Now, a -45 can be expressed as -1 times 45, which means we're taking the square root of -1, which we know by our previous definition is I. So what we're looking at here is a positive or negative I times the square root of 45. We could simplify inside of our radical because 45 It's not a perfect square, but there are some numbers in there that we can pull out. 45 is 9 times 5, and 9 is 3 squared. So we can pull out that 3, and our final answer would be positive or negative 3i times the square root of 5. If this seems wildly strange, it's because it is the first time that you are seeing use of the imaginary number. We're going to be working with it for quite a few lessons, so it will be made more clear to you. I have a final example I want to show you here. This is a whole expression that is squared. To solve this, we would try and isolate that squared expression. It's really not just one term. And we would do that by first subtracting 10 from each side and then dividing by 2. And now you see that that term, which is really a binomial, is squared. Then you would apply that square root property, which means you're looking at w plus 3 is either the positive or negative root of negative 4. Now negative 4 could be expressed, that square root of negative 4 could be expressed as I times the square root of 4, because we're working with the root of a negative number. And that radical, we can simplify that sum because the square root of 4 is 2. And let's isolate w, subtracting 3. Now you can't subtract 3 from 2i, those are different terms, so it'd be a negative 3 plus or minus 2i. Alrighty then, we are going to wrap it up here. Thank you and good night.